This is a solar PV workshop presented by the School of Environmental and Sustainability Sciences at Kean University in New Jersey. The workshop is sponsored by Constellation, an Exelon company. Photovoltaic effect is a process that converts solar energy directly into electricity. The discovery of the photovoltaic effect is generally credited to the French physicist Edmond Becquerel, who found that electricity increased when the silver plates in a wet cell battery were exposed to sunlight. Afterward, many scientists observed that electricity was generated in a solid material such as selenium when exposed to sunlight and made selenium solar cells. However, those solar cells had very low efficiency. It was not until the 1950s that the breakthrough occurred in developing modern, high-efficiency solar cells. A team of scientists from the Bell Telephone Laboratories in New Jersey produced a device using semiconductors, silicon slices that were much more efficient than earlier devices in producing electricity from light. The mid-photo shows the Bell Labs PV researchers Pearson, Chapin, and Fuller measuring the response of an early solar cell to light. They had succeeded in increasing the conversion efficiency of their silicon solar cells to 6% in 1954. In 1958, solar cells were used to power a small radio transmitter in the second U.S. space satellite, Vanguard 1. From then on, PV has been widely used as a power source for spacecraft. The best silicon PV has now reached 25% in standard test conditions. How can electricity be produced with silicon? We have to check silicon's special crystalline structure. The silicon atom has 4 electrons located in the outside layer that covers the nucleus. Each silicon atom provides an electron to form a covalent bond that binds silicon atoms. Many silicon atoms are bonded together to form the crystalline structure, shown in the left figure. When sunlight hits the silicon crystal, the energy in light could free some electrons from the covalent bonds. Many free electrons, therefore, form the electricity flow. The car parking analogy of conduction processes in a semiconductor is shown in the right figure. Each car represents an electron. There are 4 cars on the ground floor in a valence bond. No car can move around. Once there is energy lifting a car to the conduction band, the freed car can move around. Also, this leaves behind a hole that allows cars on the ground floor to move around. Conventional PV cells consist of 2 thin layers of silicon, known as P positive type and N negative type silicon. N and P-type silicon are made from modified crystalline silicon and always joined to strengthen the PV effect. In the right figure, A regular silicon crystalline structure is shown within 2 dimensions for simplicity. The light provides enough energy to promote one of the electrons into the conduction band, where the electron, red dot, is free to travel through the crystal and conduct electricity. When the electron moves from its bonding site, it leaves a hole, white dot, a local region of net positive charge. Figure B is an N-type silicon formed by doping the silicon with trace amounts of phosphorus. Each phosphorus atom, big green dot, has 5 valence electrons, so not all of them are taken up in the crystal lattice. Hence, an N-type crystal has an excess of free electrons. Figure C shows a crystal of P-type silicon created by doping the silicon with trace amounts of boron, big blue dot. Each boron atom has only 3 valence electrons to share with neighbor silicon atoms. There is 1 valence bond with only 1 electron and a hole. Hence, the P-type crystal contains more holes than conduction electrons. Through adding more free electrons and holes, PV cells can produce more electricity. This figure shows the configuration and PV effect occurred on a solar cell. A silicon solar cell is a wafer of P-type silicon with a thin layer of N-type silicon on the front surface. When sunlight with enough energy penetrates the cell near the junction of the 2 types of crystal and encounters a silicon atom, it dislodges one of the electrons to the conduction band, which leaves behind a hole in the valence band. An electron-hole pair is formed. The electron promoted tends to migrate into the layer of N-type silicon, and the hole tends to migrate into the layer of P-type silicon. The electron then travels to a current collector on the front surface of the cell and generates an electric current in the external circuit. You can observe the current with the ammeter in the external circuit. Finally, the electron reemerges in the layer of P-type silicon where it can recombine with waiting holes. If the light is strong enough and constant, there will be many electron-hole pairs formed, and a constant electricity flow in the external circuit will power the electric device connected. Overall, the solar cell converts the energy in light to electricity power in this process. Currently, there are several silicon solar cells made or in development by industry. Most efficient solar cells were made from extremely pure monocrystalline silicon, that is, silicon with a single continuous crystal lattice structure having virtually no defects or impurities. Its energy conversion efficiency could reach 20%, meaning 20% of the solar energy collected on the surface of the solar cell can be converted to electric power, which is much higher than earlier PV cells made. However, the monocrystalline silicon PV cells are also very expensive because making them is slow, requires highly skilled operators, and is labor and energy intensive. In order to reduce costs and improve efficiency, many new approaches have been developed during the past 30 years or so. These include cells using polycrystalline silicon, which is shown in the figure in the middle. The polycrystalline silicon consists of small grains of monocrystalline silicon and is easier and cheaper to manufacture than the monocrystalline. Certainly, it is less efficient because light-generated free electrons and holes can recombine at the boundaries between the grains within the polycrystalline silicon. However, with some improvements, the commercialized polycrystalline PV molecules can now reach efficiencies of over 15%. Also, solar cells can be made from very thin films of silicon with a special layer of gas, such as silane, SiH4, in between P and N-type silicon crystals. This type of PV cell is called thin film PV. The gas layer can produce free electrons and holes to generate electricity, the same as the crystalline. The thin film PV is cheaper and easier to make because it uses thinner crystalline silicon, but its efficiency is lower than both mono and polycrystalline solar PV. PV modules are now widely used in countries across the world to provide electrical power in locations where the conventional grid systems are not accessible. Batteries are installed with PV cells to ensure continuity of power. You could find many of those applications of PV cells. Some examples are shown here. We use solar PV cells in different sizes to power satellites, streetlights, RVs, fountains, parking meters, etc. Especially in developing countries or rural areas, grid electricity is usually very expensive. PV, therefore, can be highly competitive with other forms of energy supply. In those countries, many of them developing countries, PV use is growing very rapidly. In places where grid electricity is easily accessible, the PV energy systems can use the grid as a giant battery. The grid can absorb surplus PV power, making it available for use by other customers and reducing the fossil fuel use to generate electricity. When the output of the PV system is inefficient at night or on cloudy days, the grid can provide backup energy for home use. Such systems became very popular in the U.S. Many families adopted solar PV systems to save the environment and money spent on energy bills. PV arrays can also be integrated into the roofs and walls of commercial, institutional, and industrial buildings, which are normally occupied during daylight hours. Certainly, there are large, centralized PV power systems built to supply power for local and regional electricity grids in many countries. Those standalone PV plants are economically advantageous in the large scale and can be located on sites with strong solar radiation. However, the electricity produced has to be distributed by the grids, which requires additional equipment and raises electricity prices. In addition, centralized PV power systems need substantial areas of land and therefore influence the wildlife in those areas. Even with the many challenges of solar PV application, the price of solar modules and PV systems kept dropping gradually in the last 20 years. The capital investment is also dropping. This contributed to technology development and a large-scale production of PV cells across the world. Compared to other renewable and non-renewable energy systems, the capital costs of solar PV systems are still relatively high, but their operation and maintenance costs are extremely low. In the last 10 years, the world's installed PV capacity grew rapidly. In this figure, you can see that the solar installed capacity increased 2.3 times in 2015 compared to the 2010 level. Meanwhile, the PV production rate also doubled every 2 to 3 years. Almost 50% of PV modules are produced in China. The rest are produced in Taiwan, Europe, Japan, and the USA. Solar energy has become a very promising market in many countries and regions. The International Energy Agency projected the PV share of world electricity production reaching 11% of assumed demand of 40,000 terawatt-hours by 2050. The wide application will reduce environmental impacts related to energy production industries and promote sustainable development of human societies.